We're talking today about large-scale graph analysis, specifically with Akka and Scala. Just a little intro. Been coding for more than 10 years, always full stack. Been working with graphs for about 5 years now, and I work in the big data space for Capital One. We basically build data products. A little bit about what I hope you can get out of this talk. So we're going to start a little bit about the need, why we actually built a graph at Capital One, some of the requirements that we had, and then go through 2 different architectures of how we thought about implementing this. This would be sort of a naive implementation and not anything that would be robust in production, just as an example of what we've been thinking through and what we've built. And then a couple of thoughts about what else can be done in order to improve those things, so optimizations, as well as what's next after that for us. So starting with the need, it's actually a very simple ask, and it's surprisingly difficult at an enterprise. The need is, get me some data. Now, we're going to talk a little bit about why that's difficult in a second, but first, a couple of the premises about getting people some data. Well, they want the data to be already integrated, because it turned out that at least at the company that I work for, people were spending an inordinate amount of time just joining tables again and again and again. Second thing is that they want to get the results fast, right? So they don't want to sit there and wait for a query to finish processing and then get the data. They want to see the data that they want immediately. The thing after that is that they think in tables. They don't necessarily think in graphs. And some people do think in graphs, but that's not a majority of people. Most people think in tables, and they want the results in a tabular format. And it should be usable with their own tools. So you can you can plug Spark into it or H2O, or if you want to do something else, you can do that with the data. And last but not least, they wanted to think about the data, or they wanted to use the data in the way that they think about it. So Capital One is a bank. We have accounts, we have customers, we have transactions, we have statements. Why not have the data be represented in the same way? So that was the need. And the problem is that with a lot of data, there's a lot of problems. We have a lot of data, right? We have a lot of ETL that produces more data. And it's not in one place. We have multiple data warehouses. We have a data lake. We have all these source systems or pieces in the pie that basically generate data. And there's a data overload at the end of the day. And so what you want to do is you want to get a situation that doesn't look like this. You want it to get a little bit more like this. But how do you get that? And we'll talk a little bit about that in a second. But what we did is we decided to build a graph. In this case, a distributed time series graph with Scala, Akka, and Hbase. And actually, that's our little logo for it. It's called Athena. And it's like a database, but it does a bit more. So first off, you get to design the graph schema, or the model, if you will, in a visual interface. It's an ontology. It's basically saying the what is of the graph. So what are the things in the graph? In our example, there are customers, there are transactions, there's accounts, there's things like that. Once you do that, it actually automatically knows how to connect to different sources, grab the data, bring it into the graph, and make it available to you under that sort of business language that we just talked about. You can run large-scale computation on it. And it stores the data in time series. It deduplicates the data and provides you an API, so you can use it whether through programmatic interface or a REST API or whatever way you want to use the data. You can get the data, which is the original of what we wanted to do. So why a graph? Well, a graph is already integrated by nature, so we get the joins out of the way. If we give labels to nodes, then we've already made the second step towards a business language. So now a node that has a label customer, we know that all customer information is aggregated on that node. It can easily evolve over time. There's no schema, and it's relatively easy to migrate a graph. And it's efficient querying. So those are some of the reasons why we decided to go towards a graph. And if you want to think about it, there's an enterprise term for this. It's a semantic data lake. Right? So it's one step forward from a data lake. It's basically getting the data into some sort of semantics or ontology base. Let's dive in, because that's sort of a preface. Now we want to go into code and actual implementation and things like that. So we're going to look specifically at pattern matching on graphs today. And this is sort of a query language that we've created internally just for the sake of doing pattern matching. The idea is pretty simple. You start with a node label, so that in our case could be a customer or an account. And then you say the properties that you care about, and those are within square brackets, and you have some sort of comma. A dot represents an edge, so some sort of relationship between that node and another node. And then you have another node label. Now that could be the same as the first node label, but there would have to be an edge between them. Once you do that, if you wanted to illustrate it, you basically get these multiple steps. So pattern matching in graphs is really about breaking down the pattern into multiple steps that as you're traversing the graph, you're going to discover these different things that fit that pattern. And if they do fit that pattern, then you take the next step until you finally reach the end and you say, I've found a result that looks very much like the pattern I was looking for. Let me proceed because this is an actual valid result. The data model in Hbase, I don't know, how many people here have used Hbase? Show of hands, very few. Okay, so it's a sparse table matrix. I'm not showing everything that actually exists within an Hbase table. There are things in here, for instance, where there's a value Ben, there's also a timestamp, which is also used to version, and there's some labels so that you can do things like security around it and so on. But if you wanted to think about it, then it's a NoSQL store, and you have this row key, and you get to define column families. And in a column family, you can have as many columns as you want. So those are called qualifiers. So our data model essentially takes every node in the graph and says, you have two column families, properties column family, and an edges column family. Under properties, we'll store all of the values or the key values that relate to you. And under the edges, we're going to store all of the edges that you link to. We also do this as a table for every label in the graph. So if you wanted to think about it, if I defined in the ontology or in this visual organization that I described before, if I was talking about customers and accounts and so on, we would have a table for each and every one of those. So now what you get is per table, all of the row keys only refer to things that exist within that label. That's going to be important for what we're going to show next, which is actual different types of consumption architectures. So this is the first one. And what's nice about it is that essentially you get to distribute your processing of the graph very nicely with Akka and Scala. So we start by parsing the query, which is, again, a pattern match. We build an AST out of it. And then what we do is essentially have a queue or a list of vertices that need to be visited by the Akka actors. And as they're going through this queue or list of vertices to visit, they're emitting results once they've found a pattern. Now, we're going to dive into the code in a second, but this is vertex-based. That's not new. Prego does that. Think like a vertex. It's message passing, obviously, because it's Akka. There's a streaming data flow paradigm. We use Kafka as a mediator for results because what we wanted to do is if you want to start emitting results in a stream from a graph processing, then you need some way to capture that. And people might want to replay that result set. So we decided to use Kafka as a thing that captures those results. The underlying algorithm is depth-first search. And if you remember, we talked about getting results fast. That's one of the reasons. Because if we did breadth-first search, then we would have to wait until we've covered the whole breadth of the graph until we produce results. Depth-first search allows us to get, oh, I have a pattern match. I'm going to emit the results immediately. And the query that we're going to look at is something along that line. So account, and then get the account ID, and then match to some transaction that belongs to that account, and then get the transaction amount for that. So starting from the actor system, we start off by basically we take a query, and we split it up into the different steps that query goes into. For each one of those steps, we basically create a pool of actors using a round-robin pool for Akka and store it within a hash map that basically stores a reference to all of those actors, or to, in this case, the router itself. Once we do that, we basically start with a scan on the Hbase table that is the first step of the graph. Okay? So in this step, we're basically saying, get the current step where we are on the query, and then we're going to scan that table, and as we're getting different nodes from the table, we're going to send those nodes to our pool of actors that belong to that step with the query and the query iterator, which essentially provides some sort of path iterator. If you can think about it, there are different steps in our query, so you can move forward and you can move backwards. And what that does is essentially starts the processing of the graph itself. So very much like the top left here, you have a queue or a list of vertices that you need to visit. Those are generated by the first scan. And then you have different actors that in a round robin are receiving those vertices and are going to do something with them. And we're going to take a look at that. So this is the node actor. Okay? And what it does is basically receives a vertex. And if it has some data that it needs to store, or if it has already some data, then it's just going to continue getting that data. And if it doesn't, then it's going to create some sort of hash map to hold the data that you might want, so all those properties that you asked for when you were asking to do the traversal. It's then going to say, is there a next step to the pattern? If there's a next step, then let me go through the edges of that node and emit those vertices to the next set of workers. And if there isn't, then I've reached the end of a pattern, and now I can emit this result. Right? So depth first search. I started with a node. If there are additional edges that match this pattern, I'm going to proceed. If there aren't, I'm just going to return a result because I'm obviously part of the result set if I've received a vertex. So when it sends the vertex back to the sender, it's actually sending it over here to the original master or master node, where it's basically getting the vertex and it's taking these step workers and it's going to send to the next step, to the next pool of actors that manage that step. It's going to send them those set of vertices. So if I were to try and visualize this, we get a query, we scan the first table. Once we've scanned the first table, we generate basically an edge list or a vertice list that we need to visit. We have groups of actors or pools of actors that basically take this queue and get it. And as they're progressing, they're basically moving from one step to the other until finally they say, oh, I'm at the end of my path. Let's push this result to Kafka. So initial tests of this are roughly 8,000 results a second. For up to 3-hop queries. Meaning that if I did a pattern match, I would start with node label 1, I would go to node label 2, I would go to node label 3. With that 3 hops, that's what we've managed to see as initial tests. But that's highly dependent on Hbase. So some of the benefits of using Hbase is that it's HDFS under the hood, meaning that we already have a resilient distributed store of data. Hbase is also distributed. It can optimize itself to load things into memory as needed. But the problem with this is that Hbase becomes a bottleneck. Because of the design where for every node that we visit, we need to go and get some information from Hbase, this is going to be a bottleneck for us. In addition, messages flow through the master, as we saw, right? In the actor, we actually sent the next vertex to visit to the sender, which is the master. Now, in Akka, actors themselves are not optimized for routing messages. That's why we have routers. They've been built specifically to do that. So it's not a wise idea to send everything through the master. But because we wanted to segment the workers based on the steps, we had to do that. Right? The master itself was the one that contained all of these different groups of actors that needed to do that. So what can we do to improve this a little bit? Well, we can reduce the number of gets to Hbase. We can, instead of saying for every edge we're gonna do one get, we're gonna group all of the edges per node that we visited, and then make one get for all of those things. We can also do the alternative and do a scan, but then that introduces some latency because we need to wait until we've had quite a few nodes to visit until we initiate the scan. One thing you can also do is, of course, lift things into memory within Hbase, and that will improve performance. And you can say, OK, I'm going to use Kafka not only as a place to get the results from, but I'm going to use it to cache. So I can give it some sort of lifespan where I'm going to keep the data in there, and every time that somebody hits the same query again, I'm just going to replay them the same topic, and that will allow me to not have to traverse this again. We can also add workers to the steps dynamically if need be, if we're seeing that they're getting too many messages to process. From a reliability perspective, Akka does not actually support, it implements at most once out of the box for delivery, which means that for net splits or faulty nodes or things like that, you're going to lose results, right? I'm traversing the graph and I get to one actor and that actor wants to send edges to the next actor and all of a sudden it can't reach it. So what happens to that message? Does it just go away? Am I not going to get that result? That's going to be a major problem. Well, luckily there are many implementations of at least once delivery and exactly once delivery within Akka. So we can go and grab that and implement it, but that would be in addition to what Akka implements natively. So we know that the major problem with this one is that its bottleneck is Hbase. You have to continuously go get the information from Hbase. So what if we just lifted the entire thing into memory? This one is relatively similar, but it's different in the way that instead of going through a queue of getting all of this data from Hbase, we actually have the entire graph in memory. The messages that are being passed, whereas before we were passing vertices, so this is the next vertex for you to visit, the one that we have now is edge-based. So I'm going to send you an edge, and then you're going to do some processing based on the edge. And it's a distributed in-memory graph at the end of the day. Okay, so how do you actually make it reasonable to store a graph in memory? You can't obviously fit it in one machine if you have a lot of data. And if you consistently just loaded the same data again and again and again, you had to partition it in some way. Well, luckily, Akka pulls through because it has a consistent hashing router. And what's nice about consistent hashing is it basically says, if you add more actors or more buckets or places where I can place this data, I'm not going to have to move every single key in the hash table. I'm only going to have to move k over n, which is essentially the number of keys versus the number of ones that were, the set of keys that were changed. And that's on average. But that means that we can efficiently, or relatively efficiently, start to load this entire graph into memory by using this consistent hashing, where if you imagine these buckets being servers or actors, each one of those actors is holding a bunch of those nodes in memory. But if it wants to then, if now I'm going to try and find this other node, I'm just using this consistent hashing actor to go to the next step, and it knows where to go to because of that consistent hashing. And of course, this router could easily be a cluster-aware router, because that's natively implemented within Akka. So if you think about it, the consistent hashing pool is sort of the graph address book. It knows, or through that algorithm, we know exactly where the nodes are stored on different actors across the cluster or across whatever servers you may have. Nodes on the graph have a location. It's a very simplistic one. It's just a bunch of strings that are concatenated together. And the nice thing that you'll see here is actually that you just have one router. In this case, I gave it 10 actors in a consistent hashing pool. It's called the graph. And we implement this thing, and it basically changes everything. Now we have everything in memory, and we can start to traverse the graph in memory as well. But the same idea applies. There's still data coming into Hbase, so there might be new nodes that I'm not aware of, so I have to start by scanning that table, right? If the graph is populated and everything is in memory, but data has changed in the underlying data store, which is Hbase, I still need to start from the initial scan of that first table when I'm doing my traversal. Otherwise, I might miss new data that has come in. The actor node itself only gets 2 changes. Well, the first thing is that we implement a very simplistic cache. And it says, first let me check if I have this in memory. If I don't, then let me go to Hbase and get that data. And the second thing is that instead of sending it through some sort of master actor that has to route everything, I'm actually sending it directly to the router itself, which, depending on how much you've used Akka routers in your own work, You might know that Akka routers actually don't do the routing themselves. They actually hand over their code to the different actors that are going to implement them. So what you get from that is essentially that these nodes are talking to each other. They don't have to go 2 hops to talk to the next node that they need to talk to. They just talk immediately to one another using this consistent hashing algorithm. So if I were to try and visualize this, we get the query, we scan the first table, we see what matches those labels within the nodes, and then essentially all of the actors in our system are just going to talk to one another. And these vectors are going to just continue to pass through until one of them says, yes, I've gotten to the end of a result, and now I have a result, and I'm just going to emit it. So this is really cool because so far, whether you use Neo4j or other things, those are not necessarily distributed, and you definitely don't have in-memory graph processing that is relatively efficient when you're trying to add nodes to the graph, or if one of the servers shuts down, or if another server spins up. You don't have to migrate the graph completely in order to fit that those new servers. You can just do for the portion that has changed within the consistent hashing mechanism. Of course, there's still some problems in here, but those can be relatively, there's definitely ways to go forward with that. So initial tests for the 3 hops show us roughly 75,000 results a second. And that's after the first load into memory. So the way that this works is essentially, if you go back to here, again, if I don't have the vertex in memory, then I'm just going to go and get it from Hbase. So once I have everything in memory, then it's just much faster. So this number is basically after we've loaded everything into memory. The messages go directly between actors, which means that it's much more scalable and performant. And we only use Hbase when the node is not in memory, or an actor dies, and now you need to have a new actor that represents that set of the hash bucket. And then you'd need to load from memory again. The reliability is still the same as the first architecture, because we only have at most once delivery, but you can get to that exactly once delivery that we talked about earlier. And there's one question here, well, what about if I just loaded the entire graph into memory? Would that be nicer? So I'm actually going to show a quick demo. Welcome to Akka Graph. And I'm going to load a database into memory. What it's going to do now, so this is an actually slightly more improved version than what I showed in terms of the code. So it does load everything into memory up front, and it does that by scanning the Hbase tables and then just putting them into memory. Oh, sorry, 1 second. There's quite a lot of data in there, so I need to give it just a little bit more memory. How much data in here? I'll tell you in a second. It's going to show. Sorry, I can't hear. Oh, yeah, larger. So remember that each of these nodes has properties in them. So it's not only storing the reference to the node itself in memory, but it's actually storing the data of those nodes. In this one, we have roughly 727,000 nodes and 1.2 million edges. And what we can do is we can start by a simple query, right? We can say, let me get this account and the account ID, and I'm going to get the transaction and the transaction amount. And obviously, less efficient than pushing it into Kafka, but I'm just printing this into screen. And these are all results of things that have basically been produced from that query on the graph, where all of these nodes are just talking to each other. So if I wanted to just show everything that's in the graph, and of course this is fake data, well, many more fields than what I just showed, right? But this is just producing those results and allows us to see sort of the power where we can easily match this, or we can easily do pattern matching and get all this data back And this entire graph is in memory, and of course I can make it distributed, I can make it cluster, and I can manage the idea of a node dying or a node coming back up. You might have noticed that there's a question mark of when does it actually end processing? And it's relatively easy for us as humans to notice that because no more data is being printed to screen. But for a machine, it's a little bit more difficult. So a couple of ideas there. Well, we could count the number of nodes that we intend to visit and check that against the number of nodes that we have visited. And we could also do that per step. But that's not that great in a non-deterministic system. We could have a race condition of some sort where something actually gets the count up and it matches the number of things, and we think, oh, this is the end of the query. But if we actually go towards implementing exactly once delivery, then we can actually get a distributed task list of the nodes to visit in the memory within the actors themselves. So if I'm an actor and I'm trying to think, okay, well, I've sent these edges to this other actor, and I'm waiting for it to respond with the list of edges that it's visited, I can hold that in memory, and until I've resolved all of my tasks that I've given out, I'm not going to finish. Now, that might sound like ask within Akka, but there are some problems with implementing it that way. There are better ways where we can just do this with message passing with tell instead of ask, and get better performance so long as you're managing this task list. And it doesn't require that you have to hold the entire graph in memory, of course. It's just the task that you sent out. And actually, quite nicely, we can see in here, so I've given 50 actors to this graph. Each one of them has a set of load to them. So based on the distributed hash, they all got different nodes. So this one has 16,000. This number of queries or messages that passed through it, and this is the number of results that it produced. And we can use that information to further optimize. So we'll talk about that in a second. Okay, so what next? Well, how about getting rid of Hbase altogether, right? We're using Hbase right now to store the data. We do need a persistent store, but do we have to rely on it being the first thing that actually gets the data, or could we just push all data first to the Akka graph and then have that persist? Well, why don't you mutate the graph in memory first, maybe implement the wall, a write-ahead log that's very similar to what Cassandra and Hbase do. Maybe we can use Akka persistence for this. Maybe we use something like Hbase or Cassandra or something else, but just to store the actor state, not necessarily to store the data aside from that state. Another interesting thing that we could do is you looked at some of those statistics about adding or the number of messages that flowed through or the number of nodes in the graph that I'm actually holding as a single actor. Well, we can optimize based on that. I could say, I don't want to hold in a single actor more than X number of nodes. So if I find that, let me add another routee to the consist capital one. And there's many more options for what we can do here. So to finish up my talk before we go into sort of a question and answer model, we are hiring. We build data products. If you're interested in things like this with Akka, Scala, and Play, it's a shameless plug, but here we are. We are hiring people. And now for questions and answers. I think we have roughly 10 minutes left. So that was it. Yeah. Sorry, I couldn't hear you. So it will be, it's roughly 200 billion nodes. Yeah. 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 Yeah.
So you're writing your own query language. What about like something like Tinkerpop or one of those?
Yeah. Yeah, so the question is actually one that I guessed we should address. So why not Tinkerpop? Why not Gremlin? Why not GraphX? Why not all these things? Well, I think that Gremlin as a DSL for traversing graphs is actually a great DSL. Under the hood, though, it's relatively tied to Tinkerpop as a stack, which doesn't include time series, and it doesn't do streaming data flow. It does do data flow, but it doesn't do streaming data flow in the sense that I can't just start to emit results immediately. They have to be batched up and then deliver the results. So will we ever go into a DSL that's like Gremlin or like Cypher or anything else? Yeah, I think that's definitely a possibility, but we haven't implemented that yet. From a graph processing frameworks, I mean, you can run PageRank and connected components and all these things, but remember that our premise was, let me get the data to the people first, and then they can do whatever they want with it. Eventually, we will implement these graph algorithms, but first, let's pattern match and get people the actual data that fits what they were looking for. Other questions? Yeah.
Like you have a slide on how to detect query finish. Like, do you keep track of, like, do you have a map to say this is my outstanding query, and then, like, if an actor is non-living actor, right? So if you're processing 10 query at the same time, then do you keep a map per actor to say I have 10 active queries, and then each of them I am going to 5 address, for example, so I'm keeping a map, or like how do we keep track of that?
Yeah, that's a good question. Let's see if it's in here. Yeah, this is just a very, illustrative example. But at the master or the query engine actor, we would store the query jobs. Each query job essentially creates a query object that has an ID. That query object, when it's getting past the vertices in here, could actually, and that's not implemented on the screen, but I'm just showing it in theory, that query object could be stored in some sort of task list. So per query job, here's my task list. And then I'm waiting for all these tasks to be finished. Once it's finished, I'm going to say, I'm done with all my tasks for this query job. And then the master knows, OK, well, it's resolved the entire query. I can now say, this query job is done. I'm still going to produce the results in a stream, but I'm at least going to check whether or not it's completed its entire traversal. Does that make sense?
You said you use some visual tool to define ontology. So what tool do you use? And is that all ontology, or what kind of ontology is it?
Yeah, so we built our own, just internally using D3 and a bunch of other things. Right now, it doesn't produce an OWL, but we want to move to that. Some of the reason is just because OWLs don't inherently connect to the data source that we want to pull the data from. So the logic within Athena, which is what I've been talking about, is that you want to connect, you want to build the ontology using fields that actually exist out there in the different data sets. So we'll eventually move towards OWL, but we don't have that ability yet. And then there was another person right there.
Do you run this on your own infrastructure, or do you use some sort of cloud solution such as Amazon?
Yeah, so EC2 is where we're on. We've actually migrated a lot of things into EC2 recently. Other questions? Okay. Thank you.